Today's seminar is focused on pores. The shape and the size of the pores determines the properties of the porous material. It is therefore necessary to characterize the pore space. This can be done with porosity, pore size distribution, tortuosity, and many more. But some of these parameters are not so straightforward to understand as they initially seem. Welcome to our online seminar on what is a pore, understanding porosity and transport in porous materials. So my name is Jürgen Becker and I am the head of Master Markets support team. I was part of the founding team of Master Markets, so I've been with the company since the start. Before that, I was a research assistant at Fraunhofer ITWM here in Kaiserslautern, which I joined after finishing my studies of mathematics in Bonn. So for example, everybody says pore size, but depending on how it is determined, it can mean something different. When you measure pore sizes with MIP, you do not directly measure a pore size. The device measures pressure versus the mass of the mercury. And then it computes the size distribution using the Washburn equation, which includes some assumption, for example, the assumption of a cylindrical pores. And of course you can calibrate for non-cylindrical pores, but the resulting pore size is still an interpretation of a measurement and not a direct geometrical distance between two pore walls. And similar, with a flow porometer, you measure pressure rate and flow rates. A bubble point test measures the pressure needed to get an air bubble across. You can use glass beads to measure percolation paths, or even NMR measurements to identify pore sizes. But in fact, all the measurements are indirect and will probably give different pore size results for the same sample. So if we look not at measurements, but at models, then in contrast to the measurements, for example, pore network models, they have a very clear geometrical definition of pore sizes. But they do not show the real pore geometry. The true pore geometry is accessible if you use 3D structure models that show the full complexity of the pore shape, like we have them in GeoDict. For real materials, you can get them with the help of a micro-CT scan. Or you can create virtual models with GeoDict. And here now we can analyze each pore geometrically, but the question is how to define the pore size of an arbitrarily shaped pore space. And in this seminar, we will present the options that GeoDict offers here. So the question arises also here: what is a pore? And how can we make sure that we compare numbers with the same meaning when we compare them with a measurement? So this seminar will consist of the following parts. First, my colleague Anne Blumer will show how GeoDict defines a pore and pore sizes. Then in the second part, she will demonstrate how to compute these values with GeoDict for two sample structures. In the third part, I will demonstrate with GeoDict's ability to compute tortuosity with respect to different definitions of tortuosity. And last, there will be a Q&A section. Of course, you can ask questions anytime during the seminar in the chat. We will either answer them directly in the chat or answer them later in the Q&A session. So please, Anne, start with the first part.
Hello and welcome to the online seminar, What is a Pore? Understanding Porosity and Transport in Porous Materials. My name is Anne Blumer. I studied mathematics here in Kaiserslautern, and in 2022 I joined Master Market as application engineer in the support team. In GeoDict, different methods are available to determine the size of a pore. Before describing them in more detail, we answered the following questions. What is a pore? And what is a pore body? And what is a pore throat, or also known as pore neck? Structures in GeoDict may consist of solid voxels and non-solid voxels. The non-solid parts are also called pore space. The pore space may be empty or filled with a fluid material. The transition from the term pore space to the term pore is not that trivial. For a pore space that is convex, for example, it has the shape of a sphere, the whole pore space can be called a pore. But for more arbitrary shaped geometries, we need two other definitions. A pore body is a relatively large part of the pore space, for example shown here, while a narrower part is called a pore throat, as you can see here. To get an idea, imagine the pore space to be a network of channels where pore throats divide larger parts of the pore space, but still connect those parts. When talking about the term pore, often the pore body is meant. However, there can also be pore space which is not connected to any other pore space. This pore space is called closed pores. Here is one closed pore in the example. But why should we measure pore sizes? Many physical phenomena occur in the pore space of a material. For example, the flow of a fluid through a media which is described by the permeability. In filtration application, this helps to determine the efficiency of a filter. It is important to understand the difference of pore bodies and pore throats. For fluid simulations, larger pore bodies are advantageous because they can carry a large amount of the fluid, but narrow pore throats limit the further transport of the fluid. If you know much about the pore space, this can help you to build a digital twin of your material. One example is the ratio of pore bodies to pore throats. Today, we will have a closer look at a battery structure and a porous rock structure. This will be shown in the second part. There are several lab techniques to measure pore sizes, and here we list some of them. One is the Mercury Intrusion Porosimetry, which is suited to measure pore throats. With X-ray micro-CT scanning, you can visualize the pores and use image processing methods. The scanning electron microscopy is similar in the output, but works different. For the Mercury Intrusion Porosimetry, the MIP, the assumption is often that the pores are spheres, which is not correct. Or have you ever seen a perfect spherical pore in nature? GeoDict provides different techniques to measure pore sizes. Today we'll present 4 of them and will later demonstrate them in GeoDict. The granulometry is a geometrical approach where spheres of different sizes are fitted into the pore space. This is done for spheres of different sizes so that each voxel has a diameter that corresponds to the diameter of the largest sphere that can be fitted into this voxel. An advantage of this method is that closed pores are also found and measured. We can observe here the largest pore body that is found in red, with the red sphere, which has a diameter of 5 micrometer. And the next larger pores are the one here in orange. It's a little bit smaller, and then this third pore body. You can observe for the closed pore that we have here a diameter that is not 0 micrometer, but somehow around 1.5 micrometer. The porosimetry is a bit similar to the granulometry, as also spheres are placed in the structure. But here there must be a path from the chosen domain sites through the structure. This means a sphere of a certain diameter could be moved into the structure through the pore throats. This is why this method is good at detecting pore throats. This is in the same example as before, where fluid comes from the left side of the structure and enters the structure. And this first part of the whole pore space has a diameter assigned of 2 micrometer, which corresponds to this pore throat here at the beginning. And you can remember from the other slide that this pore space was assigned a diameter of around 4 micrometer. And then you can see here this even smaller pore throat where the fluid has to enter. And then this whole pore space here behind has the same diameter as this pore throat here. It's around 1 micrometer. Also, this method does not detect the closed pores. As you can see here, the assigned diameter is 0 micrometer. The percolation path somehow is a bit similar to the porosimetry, but here we search for a path of maximal width. This then gives the diameter of the largest sphere that could be transported through the structure from one side to the opposite. As you see here, this is the percolation path through the structure, and it has to enter this narrow pore throat. It's the smallest pore throat. Even though the place here is larger, the width of the percolation path is limited by the size of this pore throat. Closed pores are ignored because there can't be any transport from one side to the other. As a fourth method, you can use identify pores to identify and label each individual pore by fitting ellipsoids. Here also closed pores can be found. In this example visualized are the found subvolumes before the ellipsoids are fitted, and each subvolume has a unique ID, which is visualized here. You can see that this closed pore also gets an individual ID. And now we go on to the second part where we show the 4 presented methods on a battery and a rock structure. In this live demo section, we use 2 examples to demonstrate how you can measure pore sizes with GeoDict. Here you see the GeoDict GUI, and we click on File and then Open Structure to load the first example structure. This is a GDT file, a GeoDict structure file. The structure is a cathode from a battery, which you can see here in the 3D view mode. And you can first observe your structure. You can see here the larger NMC grains in gray and the binder in black. The electrolyte is currently invisible. But we can turn the visibility on, and it is shown here in white. You can click on the 2D icon to change to the 2D view mode. And in the camera tab, you can slice here through the structure. We change the project folder under File, choose Project Folder, select Project Folder, and we select the Results folder. The computed results are automatically saved there. Please note that for this video the computations were skipped. We now uncheck again the visibility of the electrolyte to later observe better the computed results. By visual investigation, you can observe the large pores that are filled with electrolyte. The NMC grains contain very small pores. Under Analyze, select the PoreDict module, and on the left in the Module section, select Pore Size Distribution Granulometry from the pull-down menu. With a click on the Edit button, the Settings dialog opens. As always, choose first a result file name. The parameter bin size determines the range of diameters that belong to one pore class. All bins have equal bin size. Beginning with the largest possible diameter that is divisible by the bin size, the diameter is reduced by the bin size in each step. Every voxel is then assigned the diameter of the largest possible sphere that can be fitted in the pore and contains this voxel. Thus, if I is the bin number, Each bin contains pore voxels with an assigned diameter in the range comprised between I-1 times bin size and I times bin size. For example, when analyzing a porous structure with a voxel size of 1 micrometer, you can set the bin size to 2 voxels, which would result in the first bin being 0 micrometer to 2 micrometer. The second bin is 2 micrometer to 4 micrometer. If you instead set the bin size to 4 voxels, the first bin would be from 0 micrometer to 4 micrometer. Also important is the choice of the domain boundary conditions, which depends on the structure itself. With symmetric, the structure is like mirrored at the domain boundaries. The pore sizes at the boundaries are measured like they would expand over the boundary. For periodic, it is very similar, but the structure is like repeated. This may cause that a pore might not be continued above the boundary. We recommend to only use it for real periodic structures. When choosing in case, the structure ends at the boundaries, like there is a solid wall. With expert, you can assign different conditions for each direction. We check write pore size distribution as GSD file, which contains the pore size, which is the diameter of the sphere of each voxel, written into a volume field. Thus, we can later visualize the pore sizes. Then we click OK and run to start the analysis. After the analysis has finished, the result viewer opens, and under the Report tab, the characteristic diameters D10, D50, and D90 are shown. These are the diameters such that 10%, 50%, or 90% of all pores have a smaller diameter than the corresponding value. In this example, the D10 value of 0.16 micrometer means that 10% of all pores have a diameter smaller than 0.16 micrometer. The D50 value means that 50% of all pores have a diameter smaller than 0.896 micrometer. The D90 value means that 90% of all pores have a diameter smaller than 2.45 micrometer. Underneath, a detailed table lists minimum and maximum diameters, volume fraction, cumulative volume fraction, pore volume, and the differential pore volume distribution for every bin. Also, at the bottom, the total porosity of the structure is shown. The volume fraction of the pore voxels in each bin and the cumulative volume fraction, starting with the smallest pore diameters, based on the total pore volume of the structure are shown. For each bin, the pore volume in meters cubed is computed as the summarized volume of the voxels that belong to this bin. The differential pore volume for each bin is computed where both the common logarithm and the natural logarithm are shown. Under the results plots subtab, different relative and cumulative histograms can be plotted. Choose to plot volume, volume fraction, or the differential pore volume distribution in the volume histogram plot section. In the cumulative histogram plot, the red curve shows the volume fractions of the pores smaller than a given diameter, and the blue curve shows the pores larger than or equal to a given diameter. Both curves sum up to 100% for any given diameter. In the Pore Visualization tab, click on Load GeoDict Size Distribution, GSD, to load a volume field containing the pore diameters. The value at each voxel is the diameter of the largest sphere that contains this voxel and fits inside the pore space. Have a look at the small pores inside the NMC material filled with electrolyte. These pores are closed pores, which means that there is no connection to the domain boundaries through the electrolyte. When zooming in, we can hover above these pores and can observe the value of the volume field. At this pore, we have a diameter of 150 nanometers, which is 5 voxels. We can uncheck the visibility of the structure and the visibility of the volume field in the solid material IDs. Then, with the slider, you can filter the smaller pores and see only the large pores. We analyze in the same structure using the porosimetry command. The parameters of porosimetry are similar to those of granulometry, but here you have to choose the direction or multiple directions from which the fluid intrudes the structure during the simulation. In this example, we choose both the set domain sites. Please note that we set the same bin size as for the granulometry. Also, the results look very similar, but the values are different. Here, the characteristic diameters are 0.14, 0.68, and 1.59 micrometer, which is smaller than the values found with granulometry. This is because the porosimetry detects the pore throats as mentioned earlier. A certain pressure would be needed for the fluid to pass a narrow throat, and once it is passed, the area behind is instantly filled. This pore space is assigned the same diameter as the narrow pore throat, and the found diameter for the same pore space is thus smaller. For this command, we can also load a size distribution file. If you remember the granulometry result, you might now observe less orange and red parts. This means less larger pores are found. If we zoom now into the small pores inside the NMC material and hover above, we see that the values in these pores is 0 micrometer. As mentioned earlier, this is because these pores do not have a connection to the boundary. Thus, the invading fluid cannot reach these pores. To compare both result files better, we generate a combined result file. Select both files and click on Combine Results. Then, observe the plots in the combined result file. Fewer large pores are found by porosimetry than by granulometry. This can be observed in the cumulative plot at the bottom. In the upper plot, you can observe that the porosimetry plot contains more spikes than the granulometry plot. Each spike corresponds to a past pore throat, as the area behind it is instantly filled with the invading fluid. Before we have a look at the second example, we discard all structure and volume files. Click on Yes. And then we can load here with the shortcut icon, not in the results folder, but in the input data folder, the other example, the Berea sandstone. We can also observe this example in the 3D mode. And to better see the pores and the grains, you can activate shadows and show halo in the camera tab. Then we get a better overview of the Berea sandstone. We calculate the largest percolation path. We want to calculate in that direction and search for the diameter of the largest possible sphere that would fit through the percolation path. So the diameter mode is set to maximal diameter. The result file shows that the maximal diameter is 6.28 micrometer, which are 8.5 voxel. This is a good value if you want to perform a flow simulation afterwards, because it means that the structure has a good resolution. A very small diameter of less than 5 voxels is bad for flow simulations, and you would need a better resolution. The path has a length of 1175.5 micrometer or 1588.5 voxel, which is 50% more as the length of the structure in this direction. In the Data Visualization tab, we load the analytic percolation path geometry to see how the path looks and where it is located. To load the path together with the structure, load the GDT file from voxel geometry with percolation path. You can also choose to load particles and observe how a single particle would flow through the structure on the percolation path. But I would recommend to uncheck the visibility of the structure for this. And with the time slider, you can observe the particle flowing through the structure. On the same rock structure as before, we use the command identify pores. We set the input mode to use current structure to analyze the structure currently in memory. The minimal pore diameter should be 6 voxel to exclude single particles that are smaller than this diameter from the analysis. The analyzed material is the pore space. Check reconnect fragmented pores with the threshold set to 28%. I tested before and this seems to be a good threshold for this structure. Check remove pore fragments at the boundary to exclude boundary pores from the analysis. Otherwise, pore fragments could negatively influence the statistics. Identify pores results in 13,447 found pores. Many of them are very small pores, as the sandstone contains grains with some inner porosity. This is similar to the first example where the NMC grains also had an inner porosity. You can observe in the table below, for example, the pore volume statistics and the pore diameter statistics. For the latter, the percentiles are also given. From the Pore Visualization tab, you can load the identified pores as G32 file. In this file, each pore gets a unique ID and they are then visualized with different colors. As we chose to remove pore fragments at the boundary, no identified pores touching the boundaries are found. Some pores may be oversegmented. In this case, you can adjust the interface threshold to merge these pore parts before the analysis. The individual pores you observe are analyzed, and volume, the diameters of the fitted ellipsoids, and many more parameters are computed and plotted in diagrams. In the Plots tab, you can click through these various histograms and other data plots. For example, you can observe the volume histogram. The smallest pores make up 35% of the pore volume. In the result viewer, you can not only plot it in the way it is now. On the left, you can change, for example, from relative distribution to cumulative distribution. You can also change the weighting, for example, from weighting by the total pore volume to weighting by the number of pores. To weight by number, choose it from the list and click Apply. After the new histogram is computed, we can see that over 80% of the pores belong to the smallest pores. With the threshold by scalar value, you can separate the pores into different classes and load them from the Pore Visualization tab. Choose the desired value from the list. We choose volume and set the threshold method to k-means. This method automatically computes the threshold to separate the pores into two classes as entered below. More classes are also possible, but we will stay with 2. After clicking Apply, we change to the Pore Visualization tab and click on Load Pore Type Structure, Load GDT. In this way, you can, for example, as shown here, distinguish between large and smaller pores. Remember that over 80% of all pores belong to the smallest pores. This is the end of the short live demonstration. Thank you for your attention.
Thank you, Anna, for the presentation. And we will answer questions to that part later in the Q&A session. And we now come to the third part. What is tortuosity and how can we compute it? So, tortuosity is another often used measure to describe pores. And the general idea is easy. You compare the length of a path with the Euclidean distance between the start and the end point. And the more tortuous this path is, the larger the tortuosity value. But we now want to define a tortuosity not only for a single path, but for the whole porous material. And how to do that? Well, we have to average multiple pathways. But which and how to weight them, this is the trick. And if you look in the literature, you can find many different definitions. I show here an overview slide presented by Lorenz Holzer from Zürcher Hochschule at Winterthur in Switzerland at a GeoDict user meeting. And he differentiates between direct geometrical measures and indirect physics-based measures and mixed measures. So in the geometric measures, you compute the lengths, you find the shortest pathway, and then you compute the length of them. In the physics-based methods, you solve a transport equation, either diffusion, conduction, or flow. And then you look for the transport in this field and derive the tortuosity from the transport of the material through the media. And in the mixed methods, for example, you take a transport of a flow solution and compute the streamline. And the clue now is this is all possible with GeoDict. So I will now demonstrate how we can do that in GeoDict. So we first load the example that we used before, the barrier sandstone. We see here the 2D cross-section, and we can switch also to 3D visualization. Switch on a few effects to have a better view on the material. You see, this is a dense material. Of course, it's a stone. So we have a porosity of only 18% and a solidity of 81%. So the geodesic tortuosity is the first one that we want to compute. And this command is part of porodict. So we find porodict here under analyze. And in porodict, we have the geodesic tortuosity down here. We click on edit. And then we have to choose the direction in which we're interested. So here the Z direction from top to bottom. And in which material to compute the tortuosity. So we're interested in the tortuosity in the pore space. Periodicity we keep switched off because we have not a periodic structure and the pathway should not go from one side into the other. And we switch on here, and to show what this means, we can have a quick look on the user guide that you can always access here by clicking on this. This will directly lead you to the corresponding page in the user guide. And if we scroll down here, we see what optimized paths will do. So we have a large open pore. Then without optimized paths, you will get a certain staircase pattern in the voxel grid. And with optimized paths, this is optimized into the straightest way through the open space. So we switch this on, click OK, and then click Run. And as this will take a while, I'll load it. I have the example here. I enlarge this a little bit here. You see it takes 2 minutes, not very long, but too long to wait in this live demonstration. And you can find the tortuosity result here. So it's 1.1. We can also have a look at the result field here that explains in more detail how this tortuosity is computed. So we load these results. And we have to switch off the structure here, and in the volume field, we only want to see the value on the pores. So we see here color-coded from blue to red how far the distance of the pass through the pores to the bottom plane is. So blue means here we have 0 distance, and then going up here the distance gets longer and longer, and we have it color-coded for each individual voxels. In blue here we see also the unconnected pores. They're not connected at all, so they're not taken into account in the tortuosity computation. And up here on the, so to say, outflow plane, we have the highest values. And now the tortuosity is computed as the average of all the values that we have on the outflow plane by the distance, so the thickness of the material. And we can see here that the highest numbers are somewhere in the 800 micrometers. So this is a little bit longer than the distance here, which will lead to the tortuosity of 1.1 that we see in the result. So this is the geodesic tortuosity. It uses the shortest path, but it does not take into account if this path is likely to be used. So all the paths may go through very narrow passages. So this probably does not describe the transport properties of the media very well. So, and to compute a tortuosity that describes the transport of the species through the media better, we can, for example, use diffodict, which we find here under predict. And here, in the Laplace equation is solved to describe the diffusive transport of a species through the medium. In this case, the tortuosity is derived from the diffusive flux and effectively describes how much the porous media slows down the dissemination of the species. So we open here, edit, and we have to select a fluid material. Here we choose air. In fact, the selection here doesn't change the tortuosity that we compute, because this is a purely geometrical value. On the boundary conditions, we have to choose again the computational direction. We're interested in the z direction, and have to set again if we have symmetric or periodic boundary conditions on the sides. The concentration at inlet and outlet doesn't matter for computing tortuosity. This will just change the absolute value of the concentration field that the diffusion solver gets, but not the resulting tortuosity value. On the solver grid, we choose the LER solver because this is quicker on these dense materials. So we click OK, and we can click Run here, and again, I open the pre-computed results. Tortuosity by diffusion. We set this to visible again. And we get the diffusivity, but we're not interested in that here, and the tortuosity. And in this case here, I enlarge this a little bit, it's 2.14. So you see, it's a different number than we had before in the geodesic tortuosity. And so we see that although a short geometrical path exists, for the diffusive transport, this is not relevant. And the majority of particles seems to take a longer way. So we have a higher tortuosity here. And to compare all the tortuosities, we have created an app that can compute them all in a single command. So you can find this here in GeoApp General Property Prediction. There's the Compute Tortuosity app. And in the options of this app, you can again, of course, first computation direction, then the boundary conditions, take symmetric periodic here, and then you have a list here of which tortuosities you want to compute. So the geodesic we have here, and for example, the diffusion we have here. But there are also other tortuosities, for example, in the mixed ones here, you can have the tortuosity from the streamlines. Down here, you can have tortuosity of percolation paths up here, and so on. And again, I show how this looks as a result from the Tortuosity app. You get them here, the geodesic tortuosity reported. You have here the diffusive tortuosity reported, and all the other tortuosities that you have checked. And if you compare it here, the three results you see here, this 1.109 we have here, 2.14 we have here. So what can we take away from this? Be careful when someone tells you that the tortuosity is, for example, 1.5. You have to check how this was determined. And unfortunately, you always have to consider which tortuosity is relevant in your case. You cannot simply take a number that was computed anyhow. For example, if you want to describe the prolongation of flow pathways, it's not a good idea to use the geodesic tortuosity. You have to use the hydraulic tortuosity. And if you want to describe the diffusive process, then you have to use the diffusive tortuosity, because this is the tortuosity relevant to describe the transport in this case. So, yeah, with this I finish my short demonstration on tortuosity, and we come to the questions and answers Q&A session. So if you have any questions, you can post them in the Q&A field.
There was already a question posted. Maybe Jürgen, you can answer. I'll just read it out. For the battery electrodes, which tortuosity must be calculated?
Yeah, this depends on what you need. I mean, so if you're interested in the conduction, for example, in the solid parts, then you should take the diffusivity from that you get from ConductorDict. Or if you're interested in the diffusion process in the electrolyte, then you should use a diffusive, because I think this will describe the transport that you're interested in. So someone asked if we have experience of the dependence of porosity due to resolution power of the microcity. Yeah, if you compute porosity with GeoDict, you can of course only see the porosity that is resolved on the resolution. So if it's well possible that in a microcity image you have a hidden porosity. That means that what you see as a solid in your resolution is not completely solid, but has an inner porosity that is just not shown on the microcity image. In this case, of course, GeoDict will only show you the resolved porosity, and there may be some unresolved hidden porosity. And yeah, depending on your application, there may exist models that describe how much hidden porosity to expect, but you cannot, in general, I mean, the information is just not in the image. And so you always would need to have some theory about it.
Yeah, so there's another question about the pore size distribution. In the video, it was shown as volume fractions, and the question is there a way to express it in number fraction? I think it was also shown in the live demo. You can change it in the post-processing options of the result file. It is the weighting by volume or number option, and you can simply change it to number.
there's a question about how to choose the correct bin size. No, it's not always 2. It just determines how many steps are computed, and so you distinguish between pores. If you choose a bin size 2, you have all the pores between 0 and 2 are considered in one bin, and then 2 to 4, 4 to 6, 6 to 8. And if you choose a bin size of 4, you have bins 0 to 4, 4 to 8, 8 to 12. So it's kind of the resolution of your curve that you get, and you can take any bin size. And of course, if you take a bin size too large, then you just have 2 or 3 points on the curve. But if you take a bin size too small, then you can also have too many points on the curve, and then you get only spikes and don't see the general shape of the curve. So it depends on the resolution. A question: can we also compute combined tortuosity of 2 faces which intrinsically has different conductivity? Yeah, you can choose which materials. So I can compute the tortuosity in the pores, but I can also say I want to have the tortuosity in a certain solid phases or in 2 or 3 phases combined. Yeah, I mean, you can also compute them separately and somehow combine these numbers. So you're not restricted to having the tortuosity of the pore space. You can have the tortuosity in any phase computed with all of the methods. Yeah. Typically, the default is that you compute it for the pores, but you can usually switch it to another material.
And there was also a question not already answered for filtration, which tortuosity is relevant.
Yeah, I would say either with the hydraulic, if you consider if it's about flow, or the percolation path tortuosity, if you think about the particle movement. But I think the geodesic is in most cases not relevant, because the shortest path through the medium is not the one that describes the transport of anything very well. Yeah. Because it always looks through the shortcut, which is typically not the way that the either particles or flow or anything takes. And so it's you should, I think, always consider the transport related tortuosities. And if you're interested in transport problems, but usually you are. We have answered most of the questions. Also, we have reached the end of the hour. So before saying goodbye, I want to mention that we'll now have a short summer break with our seminar series, and then after the summer break at the end of August, there will be the next online seminar on complete filter flow simulation. This is not the final title. Also, the time is not set, but the date is August 26th. And the seminar topics will be how to import CAD models, how to compute and visualize flow in these CAD models, and how to simulate particle movement and deposition. With this, I thank all the participants for their attention. If you have additional questions, feel free to write an email to support@mastermarket. You can, of course, always post a question in the forum and discuss with other users and Master Market employees. Or well, you can also have a look at the user guide. Maybe a question is already answered there. So I'll say thank you and goodbye. Have a nice day.
Goodbye.